Welcome to Lecture 6, Light and Electromagnetic Wave. So as I mentioned in the introduction to this course, one of the most important things in the study of astronomy, even though it's not typically studying what we think about as astronomy, but is the study of light. And the reason is that almost everything we know about the universe comes to us in the form of light. And so, as I'll say repeatedly, but we'll start saying today, one of the jobs of an astronomer is to squeeze as much information out of the light that we get as possible. And so today we're going to start what's going to be extend over a few lectures our study of light. What are the properties of light, and how can we use those properties to extract as much information as possible out of the stuff that happens to make its way to Earth. So let's dive in. So nearly everything we know about astronomy comes from the study of light, right? Astronomy, as I claimed in the very first lecture, is arguably the oldest science because all it takes is stepping outside after sunset and looking up. But what you're doing when you're looking is you're receiving light from these astronomical objects, and you're trying to interpret that in some way. In ancient times, that was just, in even relatively modern times, that was just done by eye, right? But now, as we'll discuss, we have, computers and radar and radio telescopes and all sorts of advanced techniques. But it's all about interpreting the light signals that we get. And there are three ways that we can interact, that light interacts with matter at the very highest level. And so let's outline those, and then we're going to try to study in a little more depth how we can use each one of these three ways to try to gain insight into the stuff that's out there. So the first way that light and matter can interact is by emission. So matter can emit light. And so, for example, the sun emits light. We receive that light, and we can use that to infer something about the sun. Another way that matter can interact with light is through absorption. So one object may emit light, but another object may absorb either all or some of that light. And so one question that we're going to be interested in is how can we infer something about that stuff that's doing the absorption based upon the stuff that it does not absorb, right? And the third way that light can interact with matter is that the matter can reflect that light. And so we've obviously seen an example of this. This particular image is the phases of Venus, if you remember, which, this image appeared in Lecture 5 as well, in the context of Galileo. But in this context, we're just talking about, planets, moons, anything that's not a star. The only reason that we see it is that it's reflecting light, right? So that's obviously a very important aspect of astronomy, because if matter didn't reflect light, then the only things we would know about would be stars, right? So these are the three ways that matter can interact with light: through emission, through absorption, and through reflection. And we're going to now dig a little bit deeper and try to understand how can we use any and all of these to extract as much information as possible about the stuff that's out there. And it turns out, fortunately, there's quite a bit of hope. This is kind of putting the cart before the horse, or spoiling it, if you will. But to look at it another way, I'm trying to give you a little bit of hope that there's some value in trying to answer these questions, because it turns out that light actually carries a whole lot of information about from whence it came. And so, for example, we're going to be able to determine things like the temperature of an object, the distance that object is away from us, the speed at which that object is moving, and even such details as the chemical composition of that object. All of these bits of information are encoded in some way in the light that we receive. And so today, again, we're going to start the task of trying to disentangle that information. But in order to do that, we've got to understand the properties of light itself. So what do you know about light? So there are a few things that I want to start with at the very highest level. Light carries energy from one place to another. Okay? When an object emits light, it's giving that energy up. So when the sun is radiating all of that energy, it's losing that energy, right? That energy was inside the sun. Once it escapes and travels towards us, or towards, just out into the universe, that energy is no longer in the sun, right? So when an object emits light, it's giving it up. When an object absorbs light, it's taking it in, right? And so, for example, when you stand outside and the sun hits you, it warms you up, okay? And that's because the energy that started in the sun traveled through space and now is absorbed by your skin, and so the energy of your body increases and you heat up. And finally, when an object reflects light, it just sends that energy in a new direction, okay? So it's not absorbing it, it's just reflecting it. And so it's changing the direction, but it's not actually, absorbing it itself. Point number 2 is that light travels extremely quickly, but it's not infinitely fast. So I mentioned this before. In our day-to-day interactions and experience, we don't think about the speed of light. When I go flip a light switch, as far as I can tell, the light turns on instantaneously. Unless it's a smart light, by the way. I don't know if any of you have had this, this experience, but somehow smart lights take longer to turn on, which to me is not very smart. But that's another point of contention that we can continue offline. Light travels very quickly, and so as a result, when we're talking about how long does it take for light to travel across the room, or from a thunderstorm, if there's a lightning bolt, how long does it take for that light to reach my eyes? The distances that we're talking about are so short, and light travels so quickly that the times are essentially instantaneous. Unless you're measuring things like nanoseconds, then the speed of light is irrelevant. And so in our day-to-day experience, we either implicitly or explicitly assume that light travels infinitely quickly. But when we're dealing with astronomy, we can't do that. And there are some very important implications about the fact that light travels at a finite speed. Okay, and the reason, obviously, is that the distances that we're going to be concerned with in the study of astronomy are just mind-bogglingly large compared to distances that we experience day to day on Earth. Okay, and finally, and this is the most confounding fact, and something that we're going to spend some time talking about, is that light has properties of both a particle and a wave. And for that reason, it turns out light played a very critical role in the development of a field of physics called quantum mechanics, which is something that we will have to touch on a little bit in the next couple of lectures, especially in the next lecture, but we'll touch on it in some ways today. But light is something that doesn't fit perfectly into any category that's previously known. And so there are ways in which you can interpret it as a particle, and there are ways in which you can interpret it as a wave. Today in this lecture, we're going to focus more on the wave-like properties of it, and then in the next lecture, we'll turn and consider the particle-like properties of light. If you want more of that, you could spend a career studying that, because really this really is the nexus or it's the turning point between classical and modern physics. It is intimately tied into the birth of quantum mechanics and our modern understanding of the world at the smallest scales. And there's all sorts of modern research that still goes on in this field. So if you're interested in that, I'm happy to talk about that offline. Please don't hesitate to contact me. I will try to keep what we study here and what I quiz you on, for example, at a reasonably high level. So, I made the claim that light doesn't travel infinitely quickly, but for a long time this wasn't recognized, right? So the first person to kind of really dig into this and try to obtain a precise speed for light was a Danish astronomer whose name I will actually not try to pronounce for you, because when you start putting slashes through O's, I know immediately I will not get the pronunciation right. And so you can Google it, and I'm sure that Wikipedia or somebody else can tell you exactly how to pronounce it. But he was a Danish astronomer that was the first person, at least on record, to realize that light does not arrive instantaneously. It does take some time. And the way that he observed this was through his observations of Jupiter. And and in particular, one or perhaps multiple of the Galilean moons. And so he made the observation that when a moon of Jupiter disappears behind the planet, so again, we've got Earth here, we've got the sun, and you've got, you're staying out late at night, you train your telescope at Jupiter, and you're looking at one of these moons orbiting. And you notice, okay, at some point the moon disappears behind Jupiter, right? Because it's orbiting on the far side of Jupiter. And so he took note of that, said, okay, at this date and this time, the Jupiter, or the moon disappeared behind Jupiter. But he also knew, he says, well, what if light isn't instantaneous? What if light takes some time to travel? And so he says, well, if that's true, then light is going to have to travel from Jupiter to Earth, right? So in other words, the moon disappears behind Jupiter. It actually moves behind Jupiter, but that knowledge, seeing that happen actually takes some time because that light has to travel to the Earth. And so in other words, on Earth, when we're making this observation, when we see it happen, it's actually already happened some time ago. It just took light that time to travel to us, okay? So if Earth is on the same side of the sun as Jupiter, then that light has to travel 4.2 astronomical units to reach Earth, okay? Because the Earth is 1 astronomical unit from the sun, and Jupiter is about 5.2 astronomical units. And so there's the distance between these two, between Jupiter and the Earth, is 4.2 astronomical units. So that's fine, okay? But what happens if you wait 6 months and you make the observation when the Earth is on the opposite side of the sun? Well, in this case, the light has to travel farther, right? Now, it's an additional 2 astronomical units away because you have the 4.2 astronomical units to this point, and then you've got 2 additional astronomical units. So now you've got the same physical phenomena occurring. You still have your telescope pointed at Jupiter. You're still watching that moon disappear around the far side. But now you know that the light has to travel 6.2 astronomical units instead of 4.2. And what's remarkable is that he was able to make these observations precisely enough that he was able to determine that when the Earth was on the far side, on the opposite side of the sun from Jupiter, the event took, this disappearing of the moon was seen 16 minutes and 40 seconds later than it was seen when the observation was made on the same side of the sun. And so the implication is, well, if it took 16 minutes and 40 seconds for that light to travel across the diameter of Earth's orbit, well, it must have taken 8 minutes and 20 seconds to travel 1 astronomical unit, okay? And so in this way, he was able to determine the speed of light. And it turns out he was able to get a very good value. I don't have here exactly what the value was that he measured. It wasn't perfect, and it's been improved since then. But the modern value for the speed of light is this exact number here, 299,792,458 meters per second. It's a great number to commit to memory, but I will never actually test you on regurgitating that precise number. Very, very often, it's just rounded to 3 times 10 to the 8 meters per second, which is equivalent to 300,000 kilometers per second. So really fast, right? But not infinite, and that's going to be critically important for us. And in a lot of ways, it's really good from an astronomy perspective. It's much better that it's not infinitely fast, because if it were infinitely fast, then light would reach us immediately from anywhere in the cosmos, right? Instead, because it does take time, we're able to gain some additional information out of that light and figure things out about how far are these different objects away from us. And we can even look when things are farther away, because it takes light longer to reach us, we're effectively looking back in time farther at things that are farther away. And that actually, that's absolutely crucial when it gets to questions of cosmology, for example, that we'll study at the very end of the semester, when we're very much interested in what did the very young universe look like, what did the intermediate age universe look like, and then try to use that information to figure out what is the universe going to look like in the future. So this is an extremely important discovery. Light doesn't travel infinitely quickly. Moreover, we can measure exactly how quickly it does travel, and then we can use that information to gain more knowledge about the universe. One caveat here, or one thing to be aware of, is that this is the speed of light in a vacuum. Okay, and a vacuum is just the scientific term that means nothing, or as close to nothing as you can get. If you want to know what that distinction is about, again, you're more than welcome to contact me offline and we can talk about that. But essentially, we just mean empty space, because it turns out that when you add stuff to space, that stuff slows light down. So even traveling through our atmosphere, the light travels more slowly in air than it does in empty space, but not very much slower. Turns out gases are very low density. They don't do very much to slow light down. So normally we ignore that fact unless you're having to do a very detailed calculation. But certainly if you look at the speed of light traveling through glass or through water, it changes quite a lot from this value, and that's very important. And so when we refer to the speed of light, and certainly this number, 3 times 10 to the 8th meters per second, that's the speed of light in vacuum. And again, from an astronomy standpoint, that's usually the speed that we're interested in, because light is traveling from wherever it is, whatever star or galaxy we're observing, to us through mostly empty space. Okay, but we do just need to be aware that if it's traveling through something, it will be traveling more slowly than it would through nothing. So we've said now that light doesn't travel infinitely quickly. It takes some time. So what are some typical times that it takes? And so as usual, we start off with the Earth and the Sun, because the Earth is where we are and the Sun is our nearest source of light. So how long does it take for light to get from the Sun to Earth? Well, I gave you a clue, and not just a clue. I actually did the calculation live for you a couple of slides ago. It's 8.3 minutes, right? So I mentioned that it took light 16 minutes and 40 seconds to get to cross the Earth's orbital diameter. That means it's 8.3 minutes to get from the Sun to the Earth, about 8 minutes and 20 seconds. And so even when you look at the Sun, you're looking back in time. You're seeing the Sun as it was 8 minutes and 20 seconds ago. And so, for example, if the Sun was just taken out of existence, we wouldn't know it for 8 minutes and 20 seconds. The light that was already emitted would continue to stream through empty space to us. We would continue to be heated by that. The plants would continue to absorb the light and do their thing. It would take 8 minutes and 20 seconds for that knowledge of the Sun's disappearance to propagate to us. And then it would be a sad day. But for that extra 8 minutes and 20 seconds, we wouldn't know a thing. What about Proxima Centauri? So I mentioned Proxima Centauri in the past. It's our nearest stellar neighbor other than the Sun. How long does it take light to travel from it to us? And the answer to that is 4.2 years, quite a bit longer than the 8 minutes and 20 seconds that it takes from the Sun. And it's kind of impressive if you stop to think that if we look up and we observe the nearest star aside from the Sun, that light was emitted more than 4 years ago. So even that very nearest star to us, outside of our solar system, we're already looking back in time 4 years ago. So if that star exploded, if that star imploded, if that star, did some cataclysmic thing, we wouldn't know about it for more than 4 years. It's also worth noting that, as we've mentioned before, we tend to talk about distances, astronomical distances in units like light years. Well, if it takes light 4.2 years to travel from Proxima Centauri to Earth, that means that Proxima Centauri is 4.2 light years away. So now that we understand that the speed of light is finite but large. Let's take it a step further and consider the following question. So how long do you think it takes light to travel from one end of the Milky Way galaxy to the other? So I'll pause for a second and you can think. I won't pause for too long because either you know this or you don't, because I haven't told you. But what do you think? How big is the Milky Way? It turns out the answer is the diameter is very nearly 100,000 light years. So it takes light 100,000 years to travel from one side of the galaxy to the other. Distances are all relative. We're going to encounter distances that are much, much larger than this as we go on in the course. But for me, this is a pretty big distance. So it takes light 100,000 years to travel across the galaxy, which means the diameter of the Milky Way is 100,000 light years. Now, because light travels so quickly, at least, and as it turns out, as we'll say later in the semester, this is the fastest that anything can travel. Nothing can travel faster than the speed of light. And so this is as fast as it gets, but it's still not infinitely fast, right? But because it is so fast, it covers huge distances, at least huge distances relative to our daily experience in a relatively short amount of time. As a result, and I've made this point before, astronomers tend to talk about these large distances in terms of the time that it takes light to travel, right? Because we could talk about how many meters or kilometers the Milky Way is across, but those numbers would just be enormous. And we had this conversation several lectures back when I introduced the concept of scientific notation. And so just the units that scientists use, and frankly the units that just people in any context use, are chosen for convenience, right? We use centimeters when we're talking about things on a ruler or inches, because those are convenient units. But they would be wildly inconvenient to use in the context of astronomy. So in the context of astronomy, we use light and its speed as a way of defining our distance units. And so, as I've mentioned before, we're going to tend to talk about distances in terms of light years rather than more conventional units, for us earthbound folks, in terms of meters and kilometers. But it is important to know the conversion between these two, the relationship between these things. And so there is a precise conversion between a light year and number of meters or kilometers. And so if you ever need that number, you can look it up. If you're interested in calculating it, it's straightforward to calculate it, and I'm happy to do that with you as well. So now we get to a point that we will revisit over the next couple of lectures several times. But around the turn of the century, the 20th century, so early 1900s, there was a lot of discussion regarding the question, is light a particle or a wave? And it turns out that, I don't know whether it's, I was going to say unfortunately, I'm not sure if it's unfortunate or not. It is the way that nature is. The answer is, well, it's neither. You can't describe it accurately by saying it's a particle or by saying it's a wave. It has properties of both, and there are certain contexts in which it behaves like a particle and certain contexts in which it behaves like a wave. And this reality is sometimes referred to as a wave-particle duality. And it's one of the main principles of quantum mechanics. And as it turns out, so light is the first thing that was discovered to have this duality, where it had properties sometimes of particle, sometimes of wave. It turns out that we now understand that essentially all particles behave sometimes like waves, and all waves sometimes behave like particles. And so it really, the discovery of these attributes of light really led to a revolution in our understanding of nature at the smallest scales. And quantum mechanics was the first step in sort of that evolution. But having said that, both the wave and the particle hypotheses of light were put forth well before quantum mechanics came around, right? So even in the late 1600s, there were scientists that argued that light ought to be viewed as a particle, and there were scientists that viewed light as a wave. And so there was a fairly healthy debate in the scientific community that extended for a few hundred years before the advent of quantum mechanics, and where we came to finally understand that to a certain extent both of these views are correct, but to a certain extent both are incorrect. Neither one is complete by themselves, and so we need, as it turns out then, for our purposes, we're going to need to understand both of these views and understand when is it appropriate to view light as a particle, when is it appropriate to view light as a wave, and then use that knowledge to correctly interpret the light signals that we receive from the universe. So the basis for understanding light comes from the theories of electricity and magnetism. And so it turns out, I've mentioned a few times the notion of fundamental forces in nature. There are 4 fundamental forces that we know of in nature, and one of those is electromagnetism. And light, a correct understanding of light comes from an understanding of electromagnetism. So we'll talk in some more detail about the structure of atoms as we go on, but you've probably seen a diagram that looks something like this before. An atom consists of a nucleus made up of protons and neutrons. The protons are positively charged, the neutrons are neutral, and you might, if you kind of forgot that somehow, you could kind of infer it from the names of the particles. And then those are surrounded, the nucleus is surrounded by a cloud of electrons. And we'll talk in more detail about that, but those electrons are negatively charged, and a neutral atom is going to have equal numbers of protons and electrons so that the overall charge of the atom is zero, is neutral. Now, you could, and I have spent multiple semesters studying electricity and magnetism. There's a whole lot of interesting physics that goes in there, and there are people that do modern research on it today. But for us, one of the first things that we need to know is that opposites attract. You've heard that before. This is the prototypical example of it. There are positive electrical charges and negative electrical charges, and they attract one another. But they also give rise to things called electric fields, okay? And you could spend a lot of time studying electric fields. We're not going to do that. The important thing to know is that when you draw these electric field lines, what the lines are telling you is what is the direction of a force that would be exerted on a positive charge. So if you take a positive charge and you plop it down right here in between the positive and the negative charges, what's going to happen to it? Well, you know that likes repel and opposites attract. And so the red charge will push this positive charge away, while the blue charge will pull it towards itself. And so this positive charge, if we plop it down in the middle here, it will be forced to the right. And that's why the arrow points in the right direction. Okay. So again, we could spend a lot of time studying electric field lines, and we'll talk about them a few times here and there. I don't want to get bogged down in it, but I just want to kind of introduce you through this picture to the notion of electric field lines, and just to drive home that all it is drawing the direction. It's drawing arrows in the direction of a force on a positive charge. One important note is that if the charge were negative, then the force is in the opposite direction, right? So when we're drawing electric field lines, people had to decide, well, which way are we going to draw the arrow? And they just decided we're going to draw the arrow in the direction that a positive charge would feel a force. A negative charge will feel a force in the opposite direction. Somewhat similarly, though also somewhat differently, there are magnetic field lines. And in fact, it's worth saying that for a long time, electricity and magnetism were studied independently. And while there were similarities that were noticed, it was not understood that they actually arose from from the same fundamental force. But you can see immediately, just from these sketches, that there certainly is a notable similarity in the sense that a magnetic field is generated by a magnet, right? Or sometimes referred to as a magnetic dipole here. But if you have a bar magnet with a north pole and a south pole, There are magnetic field lines as well that tell you something about forces generated by the magnetic fields, and they look very similar in structure. If you just look at the shapes of these curves, they look very similar in structure to the electric field lines. And so, as I said, if you're studying physics, if you're getting a degree in physics, you would spend multiple semesters studying just electromagnetism. And so there's a whole lot that we're not going to be able to cover, but I mention this here because it's going to be important at least to have some of the terminology at hand as we start to understand what we need to know about light. So there are a number of fun experiments that you can do that we don't do since there's no experimental component to this class. But certainly if you took an introductory electromagnetism class in a physics department somewhere, you could do fun experiments where you have magnets and iron filings that kind of show you how the magnetic fields of the magnets induce kind of weird and even magical looking behavior in the iron. So again, we're not going to dive into that, but there's plenty of cool stuff there. So, as you might have guessed from the title slide here, this lecture is titled Light, an Electromagnetic Wave. So the claim that I'm going to make, which is a true claim, is that light is an electromagnetic wave. It's not the whole story. There's plenty more. That's why I'm not ending this lecture or the next lecture right here. But light is an electromagnetic wave. And it was described as such very powerfully by a Scottish physicist by the name of James Clerk Maxwell. And he was the first person to mathematically provide a complete description of light as an electromagnetic wave. And what that means is that it has both an electric field and a magnetic field that are coupled together in a very specific way. And that's sketched out pretty effectively, I think, in this diagram here. So you can see you have the electric field, which is represented in red here. And so it's a wave. You can see it ebbs and flows. It has maxima. It has minima. It passes through zero. And then perpendicular to that is a magnetic field that's represented in blue here. And so you can see when the electric field is zero, the magnetic field is zero. When the electric field is at a maximum, the magnetic field is at a maximum, and so on. But they're always perpendicular to each other. And this is of fundamental importance. It's something that you absolutely must remember. It's one of the most crucial aspects of light as an electromagnetic wave, is the electric and the magnetic fields are perpendicular to one another. Moreover, both of those fields are perpendicular to what's known as the direction of propagation, which is just a fancy way of saying the direction the light is traveling. So in this diagram, the light is propagating in this direction, following the arrow from upper left to bottom right. So you imagine maybe there's a light bulb out here, off screen in the upper left-hand corner, or maybe it's a laser, some light source. The light is traveling in this direction, and so the electric and magnetic fields are both perpendicular to the direction of propagation, and they're perpendicular to one another. Okay, that's absolutely crucial, defining characteristic of light. We'll talk more about the attributes of waves in general and of electromagnetic waves in particular in the next several slides. But right here, I'll go ahead and call out one of the most important properties of a wave of any kind is its wavelength. And that just means, as you see, waves repeat themselves, right? And so the question is, well, how long is that period of repetition? How long, what's the distance between one peak of the electric field and the next peak of the electric field? Or you could ask, what's the distance between one peak in the magnetic field and the next peak in the magnetic field? And the answers would be the same. So that's called the wavelength. It's that distance. And it's a fundamental property of any wave, and it's certainly going to be an important consideration in our description of electromagnetic waves, aka light. And here we just have the same sketch in the upper left-hand corner, but we've got a GIF that I hope comes through in the video. If it doesn't, then get a hold of the slides from me directly, and you can see it in its full glory. But this just shows the the propagation of the light in real time, and the oscillation of the electric and magnetic fields. So again, the electric field here is in red and the magnetic field is in blue. And so you can see if you're sitting here at this point in space at this first screen, the electric field, it changes in time, right? Sometimes it's large, sometimes it's zero, sometimes it's large and pointing in the other direction. Electric and magnetic fields are what are known as vector fields, which means that they have not only a magnitude or a strength, but they also point in a specific direction. And that's going to be important for us. And so, you can kind of, like I said, this kind of just shows you that the electric and the magnetic fields, they're always changing, but they're always perpendicular to one another, and they're always perpendicular to the direction that the wave is propagating. So that's a lot of stuff that we've covered so far already. It turns out that light and quantum mechanics and physics in general, particularly when you get to modern physics, can be pretty dense. And so if you feel like you haven't completely ingested and digested all of the content yet, you are not alone. And fortunately, to keep you interested for the rest of your life, there's plenty more where this came from. So, and I won't expect you to know everything about everything here. But let's pause for a second and back up and just think about water waves, okay? Because it turns out that electromagnetic waves have certain properties that are specific to electromagnetic waves, but they also have a lot of properties that are just generic to any kind of wave. And so we're going to talk for a second about just water waves, because that's something that we have a little bit more familiarity with. So and in particular, we're going to think about one way, anyway, of generating a water wave. Okay, and one simple way of doing that is just dropping water droplets into, say, a pond or a bathtub. I'm not sure what's actually going on in this diagram. It looks like you've got a really long faucet that's going out into the middle of a lake. So but it's easy for us to set up. So let's imagine this scenario where you're just dropping one by one these drops of water into an otherwise still, pond. Okay. Well, what'll happen is that as you drop that droplet into the water, it disturbs the lake, right? It disturbs the surface of the water. And so if that water were perfectly flat to begin with, what it's going to do is it's going to send out ripples in this circular pattern. Okay? And every time you drop a drop, it's going to send out another set of ripples. Okay? The same thing is true for electromagnetic waves and light. The difference is that instead of a droplet of water generating these ripples, the thing that generates electromagnetic ripples, if you will, that generates electromagnetic waves is oscillating charges or accelerate. Any time that a charged particle accelerates, it emits electromagnetic radiation. And in particular, if you take a charged particle, say an electron, and you move it up and down 10 times a second, it's going to emit electromagnetic radiation, electromagnetic waves, or light, which has a frequency of 10 hertz. It will oscillate 10 times a second. So exactly how many times you wiggle this electron, that's going to send out an electromagnetic wave that wiggles at exactly that same rate. So that's it in a nutshell. And again, we could spend a whole lot more time studying this. I hope you'll be thankful that I'm not going to kill you with that. But if you want more, certainly feel free to reach out. So the left side of this slide talks about then how do we generate electromagnetic waves? And the answer is we do it by oscillating charges. So let's now look at the flip side. Well, what happens if these waves have been generated? Okay. Well, what would happen if you had a bubble, or if you like fishing, imagine you've got a bobber sitting on the water and a wave comes by. Well, that's going to cause the bobber or the bubble here to move up and down with the water, right? So we've said moving the water by dropping a droplet in generates waves. Well, waves also generate motion in the things on the water. And the same thing is true for electromagnetic waves. we've already said that oscillating charges generate electromagnetic waves. But it turns out that if you already have an electromagnetic wave and it runs into a charged particle, it's going to make that charged particle oscillate. Okay? So oscillating charges generate electromagnetic waves, and electromagnetic waves generate or induce oscillation in charged particles. So it works both ways. So let's back up again and for at least one slide, mention a few explicit properties of waves that we're going to be concerned with. The amplitude. So the amplitude of a wave is just the height of that wave. And that's really just a term to remember. The only thing that I'll highlight here is that it's measured from the average of the wave, right? So the amplitude is not the full peak to trough distance, height. It's half of that. It's the distance from zero up to the peak, and that's the amplitude of a wave. We've already mentioned the wavelength. The wavelength is just the distance between consecutive peaks or troughs. Okay, so peaks, are what I refer to these top points, the highest point of the wave. The troughs are the lowest point of the wave. And so the wavelength is just what's that distance over that you have to travel before the wave starts repeating itself. And there are a couple of other properties that we're going to refer to with regularity. One is the wave speed, which is pretty self-explanatory. That's just how fast is the wave traveling through space or through water or through whatever medium it's traveling through. And then we're also going to refer a lot to the frequency of a wave. And that just means how many wave crests pass a point in space in a given amount of time, typically a second. And so if I stand, if we're talking about water waves again, and I'm sitting in the water and a peak is hitting me every second, well, then that wave has a frequency of 1 hertz. If I'm getting hit with 5 peaks per second, it probably hurts more. I'm doing a lot more wiggling, and the frequency would be 5 hertz. It turns out typical light, like visible light, for example, is going to have an extremely high frequency. And so, certainly it's such that we can't recognize that frequency with the naked eye. We can't see that the intensity of that light is changing in time. But it turns out, as we'll talk in detail here shortly, the frequency of light is fundamentally tied to the color that we experience. And so we certainly can tell a lot about the frequency just by looking at the color. So waves travel at a certain speed, they have a certain wavelength, and they have a certain frequency. And we're going to be interested in all of these properties. Fortunately, some of these properties are fundamentally connected to one another. And in particular, for any wave whatsoever, could be light, could be sound, could be water waves, could be any kind of wave that exists, there's a very simple relationship between the wave speed, the wavelength, and the frequency. In particular, the speed of the wave is equal to the product of the wavelength and the frequency. So if you know the wavelength and you know the frequency of a wave, you multiply those together and you get the wave speed. For electromagnetic waves, we've already said the speed is a whopping 3 times 10 to the 8 meters per second. So very often when we have occasion to write down an equation, again, we're going to write down C equals lambda F rather than V equals lambda F because the speed of light is denoted C. I have looked up why the letter C is chosen for that. I don't remember the answer. Very often the answer is that light has something to do, that the Latin word for light or the Greek word for light is somehow, has a C involved in it. So feel free to look that up if you're curious. But again, I want to highlight that V equals lambda F is true for any wave whatsoever. For our purposes, we're almost always going to be concerned with light because as astronomers, we're not getting sound waves from space. We're not getting water waves from space. We're getting light waves from space. And so the speed that we're concerned with is the speed of light, which is denoted C. So the last thing that we're going to talk about in this lecture, and not in too great depth, we're going to talk about it more as we go on, but is the electromagnetic spectrum. So as you've probably seen, and maybe you've even played around with yourself, white light can be broken up into a spectrum of colors that form the rainbow. So you can do this yourself with a prism, or you can let God do it for you if you wait for a rainbow to occur. But either way, it's very repetitive. The order of the colors is always the same. The spectrum is always the same. And it turns out understanding that spectrum is going to be very important to us to inferring things about the astronomical objects we're interested in. So, and before moving on, one thing that I want to drive home is that, I mentioned the order of the colors in the rainbow, if you will, is always the same. And it always starts with red and ends with purple. Of course, you could say starts with purple and ends with red, but I'm going to start with red and end with purple. And so, as we go on, we're going to talk about sort of what that means for us and how the colors, again, are related to some of the wave properties that we've already talked about. And so this is the last slide that I'll throw up here today. And there's a fair amount of information in here. And I won't talk through all of it, but I will kind of sketch or hit the highlights here for you, because this is something that we actually are going to want to kind of, I won't say commit to memory, because I don't want you memorizing this. I want it to make sense, because understanding what's represented here is going to be important for us, not just over the next couple of lectures, but for the rest of the course. And so the first thing that I want to point out is that, we experience part of the electromagnetic spectrum just, again, in rainbows, or using whether it's diffraction gratings or other ways of, prisms, for example, to separate white light out into its component colors. But it turns out that now that we know that light is an electromagnetic wave, there is a huge range of the electromagnetic spectrum that's invisible to us. So just as I mentioned that, Galileo pointed his telescope at the sky and recognized, well, shoot, there are all these stars that I never saw before. What else is out there? Once we recognize that light is an electromagnetic wave, one might be led to ask, well, are there other electromagnetic waves out there that our eyes can't pick up? And the answer is yes, definitely yes. And in fact, as is represented here on the slide, the visible spectrum is a very small part of the electromagnetic spectrum. So there are a whole lot more wavelengths and frequencies of light that we can't see than that we can. And so if we focus first on the visible spectrum, roughly speaking, human eyes are able to see light whose wavelength is between 400 and 700 nanometers. Maybe down this one goes down to 350 nanometers. Some people can see down a little bit farther. Some people, their eyes aren't quite as good. So exactly where, this cuts off, either on the low wavelength end or on the high wavelength end, varies a little bit. But this gives you a general sense of it. We tend to be able to see, the human eye can register wavelengths between 350 or 400 and around 700 or 750 nanometers. If you make the wavelength larger or shorter than that, it's still a perfectly good electromagnetic wave. We just can't see it. It's invisible to us. Okay. But as astronomers, we're going to be very interested in the extended electromagnetic spectrum, because it turns out that we can actually do astronomy just as well on the extended electromagnetic spectrum as we can on the visible. It's just we're going to have to be a little clever about how we do that, because we can't just use our eyes. And so the electromagnetic spectrum is broken up into a number of categories of differing wavelength, differing frequency, and differing energy. And we're going to be interested in all of those things. So if we start down here at the right, actually, the radio wave is the longest wavelength, which means the shortest, or the longest wavelength, the smallest frequency, and as it turns out, the lowest energy. Okay, and we're going to be, as we go on, we'll talk more and more about energy. But right now I'll tend to focus more on wavelength and frequency. So radio waves have the longest wavelength and the lowest frequency. Gamma rays have the shortest wavelength and the highest frequency. And then you've got a number of categories that have historically been identified that lie in between. So going, as we make shorter and shorter wavelengths, we move from radio waves to microwaves to the infrared to the visible spectrum, which is again quite small compared to these other ranges. Once you move past the visible spectrum and you continue to shorten the wavelength, you reach ultraviolet rays, then X-rays, and then gamma rays. And so, as you probably, if I've had to ask you, do you think X-rays have more or less energy than visible light? You probably would eventually at least guess that they have more energy, because that's why they can penetrate so well, right? That's why, X-rays travel straight through the human body, through soft tissues anyway, right? They get stopped more effectively by bone. That's why we use them in medical, for medical purposes. But the farther you go down to the left end of the spectrum, the higher energies you get, and the more penetrating these are going to be. And so that's why, visible light doesn't cause any damage to us, right? But ultraviolet light can cause sunburns. Okay, X-rays. If you had a whole lot of X-rays on your body, that can cause a significant amount of damage. That's why when you go into the doctor's office for an X-ray, they give you the lead vest and everything, so that they minimize exposure, except to the area that needs to be X-rayed. And then gamma rays are extremely energetic. And in fact, as you may or may not have heard, one of the biggest challenges to interplanetary travel, so for example, traveling to Mars, one of the biggest concerns is radiation exposure, and in particular exposure to gamma rays, because the Earth's atmosphere protects us from a lot of radiation, a lot of stuff that's just out there in space. But once you leave the Earth's atmosphere, you don't have that protection anymore. And it turns out it's not at all an easy problem to figure out, because these are very energetic things. They're not easy to deflect or change unless you have like thick atmospheres and things like that. And interplanetary space doesn't have that, and Mars doesn't have that. And so we're waiting on Elon Musk to figure that problem out. I am not optimistic, for whatever it's worth. But people are certainly working on it, so we'll see what happens. So that's where we'll wrap things up today with the electromagnetic spectrum. I would encourage you to take some time to kind of to look over this slide at your own leisure. There will certainly be some questions on the homework and on quizzes and so on related to this. There's a fair amount of material here, but I think as you sort of study it, it'll start to make sense. Most important things, I can just tell you from the outset, will be remembering what are the order of the different parts of the electromagnetic spectrum. What's the relationship between wavelength and frequency, and energy. So with that, I appreciate your attention. I'll leave you for the rest of your morning or your evening or whenever you're watching this video, and I'll see you back for Lecture 7.